So thanks for coming at these wee hours of the morning for many of you. For me, it's midday. Let me insist, and I didn't say it before, but how beautiful is Edinburgh as a city? Having said that, let's go into this. Really, really beautiful.
Especially the weather.
No, but you see, because I was thinking, of course, yesterday everywhere is beautiful with the weather like yesterday, but today it was also beautiful. And this is, I guess, more the normal weather, right? So it's really nice. All right, so yesterday we were discussing the conjecture, the Mandacena conjecture, put it in a more formal basis with these developments by Gapser, Klemov, Polerkov, and Witten. What's the idea for how to compute correlation functions? We discussed in more detail the Wilson loop, and we finished yesterday by pointing the differences of n equals 4 super n mills. If you want the original subject of the conjecture with phenomenologically appealing theories. But that I just mean theories that a phenomenologist in the fourth floor or a person more interested in physics would be interested in, right? So it's not that n equals 4 is not interesting, it's just that it does not share many features with theories of nature, right? As you may want to say. So we discussed, we said, look, these two theories really do not look alike. We have no right to believe or to wish that computing something at strong coupling in n equals 4 or at weak coupling in n equals 4 will teach us anything about QCD. And we were taking QCD as a good example of a phenomenologically motivated theory. So the goal of today is try to extend these ideas. These ideas, basically the idea of the Mandacena conjecture, this duality, into theories that may look more or may share more features with phenomenologically appealing theories. Okay? So you see that of the many things, of the many symmetries, yesterday we made a list of things, differences actually. Let me make a line here. So we made a list of differences between n equals 4 super n mills and QCD, where we were taking QCD as just as a representative of phenomenologically interesting theories. And the main differences, or the main differences I was pointing out yesterday, were in field content. The field content here is quite different from the field content there. In symmetries, that are quite different from the symmetries here. And then I was calling it in phenomenology, though this last item this last item, you see, whatever happens in this theory is basically ruled by symmetries and field content. Same here. So it's obvious that this phenomenology is going to be quite different if the phenomena in particular is ruled by this and this that are quite different in both, right? So I picked up on the Wilson loop because it was the thing that we were discussing yesterday, and we got very different behaviors, etc., etc. So we said, look, how little can this theory teach you about this one, and by conversely, how little can this conjecture teach you about the strong coupling limit of this theory? And I then soften this comment by saying, look, when you put this field theory at finite temperature, you can very well simulate it at strong coupling by this field theory at finite temperature at strong coupling. And there are many examples of this. So this was basically the point of yesterday. And so today we will try to pick on how to change this original conjecture into something that will relax or touch some of these symmetries to make it more similar to the symmetries of this. And similarly with the field content. This field content I will probably discuss tomorrow. Let's today concentrate on the symmetries, right? And when I say the symmetries, I'm not talking about the gauge group. The gauge group, as I was saying yesterday, we can work with SUNC theory here and SUNC QCD. And since there are some lattice people here, you know that SUNC QCD or SUNC Young-Mills is qualitatively very similar to SU3 Young-Mills, SU2 Young-Mills, right? So there are very good papers by people in Oxford, people in Swansea, probably people here, where they show that taking the large N limit in Young-Mills on the lattice, the phenomenology is very similar, right? The numbers do change, of course, but the phenomenology, the fact that you observe blue balls, what's the spacing, how they come, etc., all those things are qualitatively the same. So the message is, let's not fear talking about SUNC QCD, right? Let's not back up from that. Like you can say SU3, you can say SU4, SU5, SUNC in general, and you will not be losing generically important information. Very good. So let me touch on this. The symmetries that we discussed that n equals 4 has are, okay, lots of supersymmetry. It was a conformal theory. And it has this global R symmetry, right? So the main point we'll start to touch today is, okay, how to break part of this SUSY, how to break conformality, and all this by itself will break this. Okay. So if you want, let me say it this way: the moment you touch this, you will touch this, and you will touch that. Right? So we will see how. So today we will concentrate on how to extend this conjecture into examples that are less symmetric in this sense, right? And then lots of phenomenology will start to differ, right? So many phenomena that were ruled by these symmetries, they will cease to be ruled by those symmetries, and will look a lot more like the things we are used to in physics. Okay, very good. So are we okay? This is the goal of today. This is the goal of today. So let's discuss this in the following way. Do remember that yesterday I was making a small aside saying, look, all this conjecture actually came from the study of objects called D3 brains in string theory. Okay. So I guess all of you are kind of familiar with this. If not, please stop me. But the thing is, on these D3 brains is that they are extended objects. They live particularly in the type 2B string theory. So they are objects where they are word volume. It's a 4-dimensional word volume. It's like the space we live in, right? Counting time. And the field theory, when you study these D3 brains in a weak coupling regime, I mean whenever this quantity is smaller than 1, so you have NC of them, and whenever this limit is, this coupling is smaller than 1, the good description of this system we were saying yesterday is in terms of open strings that end on that object. Think it as this blackboard and open strings ending there. These open strings induce a dynamics that at low energies looks like the dynamics of n equals 4 superlemmates. That is 4 supercharge, 32 supercharges, maximally supersymmetric, 4-dimensional Young-Mills like theory. So I guess that all of you are familiar with this because this is the point that was pushed during many years. And then you may wonder, given that the type 2B and the type 2A string theory contain other D brains, particularly here D1, D3s, D5s, D7s, D5s and D7s, and particularly here D0, D2s, D4s, D6, D6s. instance, let me mention that in the theory called massive time to 8, there are what are called the 8 brains. So you may wonder, okay, what happens if instead of thinking in this way with these 3 brains, you think in the same way, but with either D1 or D5s or D7s or the other brains. Right? So the thing that will happen, let's try to induce the thing that will happen thinking about quantum field theory. Suppose that you have a field theory, and let's think just about Young-Mills. So this is just a short quantum field theory comment. Let's think about Young-Mills. So your action is something like Young-Mills or Maxwell for this. So you will have Young-Mills or Maxwell in a dimension some dimension. Okay? Right. So the point I want to make is let's count the units of this. Okay? So if we are in 4 dimensions, so the Maxwell field will always take this scaling. So the F mu nu is the derivative of this, has units of m squared. The F mu nu square has units of mass to the 4. This has units of 1 over mass to the 4, so this needs to have no units. Okay, good. Generically, then, so let's try to do this computation and not make a mistake. So this will always be mass to the 4. This will always be 1 over mass to the p plus 1. So this one will have to have units of, and help me here so I don't make the mistake. So it's is this correct? Right, so I will need to cancel whatever units come from here. That's the units of that, so I'll need to cancel this, so I will need, and this is 1 over these units. Okay? Is this correct? Good. So you see that, for example, a field theory that lives in 2 plus 1 dimensions has a Young-Mills coupling that has units of, so it lives in 2 plus 1, so P is 2, okay? Has units of mass. A theory that lives in 4 plus 1 dimensions, that is P is 4, has units of mass to the minus 1. Yep? Is that correct? So let's see, if the dimension is 4, that's a 5. So it's 1 over mass to the 5. So you need a 1 over mass. So you have a 1 over mass, and you need a mass here. Okay, is this good? Everybody follow this? This is okay? Good. All right. So let me remind you something that I'm sure most of you know, but just in case someone, just not to catch anyone out of guard here. Let's write a typically renormalizable theory. So the first one we learn. Okay? In 4 dimensions, by the way. So what are the units of this lambda? Okay, so you all know that this 5 has units of mass, then this lambda has no units. Okay? And this is the theory that we learn as renormalizable, right? So this is our first.
So
yeah.
one comment. So in Young-Mills, I agree that there's a good argument why the gauge field should have units of mass, because you have 2 kinds of terms, the a squared term and the dA, and they have to be the same.
Yeah.
But in Maxwell, where there's no self-coupling, why
No, well, but look, think it in this way. Think it in Young-Mills, but you always impose that your kinetic term is canonical somewhat, right? Right? So you may want to say, why in Maxwell I don't impose whatever is the scaling for day mu, right, such that it will leave a dimensionless gauge coupling. The thing is that if you want, in that sense, Maxwell is Maxwell alone is a free theory, right? So it's a transparent theory. The moment you couple it to a fermion, for example, there you will need to come back to this, right? But if you got in Yang-Mills, it's very clean. Your comment could be made here, right? So this I do it in other dimension, why don't I? But again, right, one is typically asking that this thing has, in all the dimensions, the same, right? The same scale. So this is the theory that we typically learn as renormalizable. And we typically learn that the theory where I replace this by is not renormalizable, right? And this will imply that the lambda is of units mass to the -2, yeah? And we learn that this theory, where lambda would be of units of mass, is typically super renormalizable, right? So what do we mean by this? That this theory will have a better ultraviolet behavior than the one we expect, right? And this theory will have a worse ultraviolet behavior than the one we expect. And even more, this theory will need to be defined with a cutoff. This theory actually will behave better and better the more to the ultraviolet you go, right? So Feynman diagrams, when computed, things that you would think a priori, oh, this is going to be divergent, then turns out not to be, okay? So that's a typical feature. Let me say it in this way, and then we say it in a nicer way. Let me say it in this way. Theories like this have a bad ultraviolet. Theories like this have a good ultraviolet and conversely a complicated infrared. Theories like this become free in the infrared, but they become strongly coupled in the ultraviolet. But that's what I mean by bad. It's not bad, it's what it is, right? But strongly coupled. Theories like this become very weakly coupled in the UV. And strongly coupled in the infrared. In nicer terms, this is an irrelevant operator, right? It takes over your UV dynamics, but in the infrared is irrelevant. This is a relevant operator. It takes over your infrared dynamics, but in the UV is harmless. It doesn't drive the thing. Very good. So I was just making this just in comparison with this. These are theories defined in dimension smaller than 4. Yang-Mills-like theories in dimension smaller than 4 will have a perturbative UV and strongly coupled IR. Generically, at least, you may want to find some and theories defined in dimension bigger than 4 will be the other way around. Okay? I hope this is clear to everyone, and probably I'm saying things that you already know, but just in case. So it's a perturbative IR, but strongly coupled with UV. And something that I'm sure you know is that this is a naive and classical analysis, right? So here I'm saying no quantum mechanics here. This will happen. This is generically happening, and as you know, in the case in which p+1 is 4, right? In dimension 4, the analysis is more subtle, and it may happen that a theory that in principle shows you no units is strongly coupled in the UV and weakly coupled in the IR, or is strongly in the IR and weak in the UV, right? And that depends very much on the quantum dynamics. And the best examples I'm sure you know them. For those two examples, one is quantum electrodynamics, and the other is quantum chromodynamics. Right? So quantum electrodynamics is weakly coupled in the IR, and then in the UV, if you just take it by itself, is a theory that becomes strongly coupled. Quantum electrodynamics, QCD is basically the opposite, or Young-Mills, if you want, is the opposite. Okay. So this operator is what this operator, or this coupling, if you will, is what you would have called in this nomenclature marginally irrelevant or marginally relevant in one case or the other. Okay, so I think I was saying things that everybody knows in one way or another. So let me try now to see how this gets translated into DP brains. Okay. So the thing is now to study not these three brains, but move from the case d equals 3 and study what happens when you study the metrics of DP brains. Right? So, by the way, for those of you who are not very familiar with this, you just have to remember that the DP brain couples naturally to a p plus 1 form that is associated naturally with an fp plus 2. Right? And these things, they do generically appear in the Lagrangian for type 2a or type 2b string theory that contains the typical Einstein term, a typical scalar field. All of them contain a coupling of this scalar field with a field that is called a Lebesgue field with 3 indexes. And then there is a variety over some coefficients of couplings to what are called Ramond fields. And these ones in type 2a or in type 2b, they are different, and they give place to these different DP brains, right, that we were discussing. So for example, in type 2b, this thing is the following. In type 2b, this is the following. In type 2a, is very similar, but with an f2 square, an f4 square, and that's it. Okay. So in type 2b, this is what will give place to d5 brains. This is what will give place to d7 brains, and this is what gives place to d3 brains. In type 2a, this gives place to D0 or D6 brains, and this gives place to D2 or D4 brains. Okay. If this was confusing, let's talk during the break, because what I was saying is either the electric or the magnetic description of the brain. So if this confused you, postpone the understanding. Just believe me that this is correct. Okay. But I can explain it better. It will just take some time. Okay, so what I will be writing now is the string frame metric and fluxes and dilaton for a generic DP brain. Okay, so people study the equations of motions that come from here. Of course, they restrict themselves to a particular ansatz where they will be taking metric, dilaton, and one of these forms, and just one of them, turn on. So they are particularly simple solutions. They are canceling this field and all the others that you don't pick in here. and they will pull out the solution. Okay, this is something that was done long ago, and I will write how that solution looks like. So let me write it.
I actually have one small thing to ask you actually. Here, I mean, we are speaking about both type 2A and B, but we know that this works for just B, but I mean, why is it that people also speak about the A case?
Good. So for those of you who didn't hear it, we know that this works for type 2B,
Yeah.
indeed. And then you are saying, well, why am I extending this to type 2A,
Yeah.
right? So the idea will be that, look, this actually is more generic than ADS5 cross S5, and maybe the way I should think about it is that, look, there are these objects called DP brains.
Yeah.
There is a field theory induced on them,
Uh-huh.
right? And by taking these two limits I was mentioning yesterday, one limit will give you a field theoretic description, the other limit will give you a metric description, supergravity description, and you will propose the equivalence of these two things, right? This proposal is really very much checked in that case, and the checks in the examples I'm going to tell you now are less stringent, but still convincing, right? But it gives you some perspective that, okay, I guess you know, but I will emphasize now, that is where you start seeing really the richness of the thing, the richness of the idea, I would say. Am I answering? Probably it will come. In principle, these DP brains, there are many things special about the D3 brains, of course, but like you propose this for D3 brains and the theory induced on the D3 brains and the metric produced by the D3 brains, you may wonder, why can't I do it for D2 brains or D4 brains, right? So why not? And the thing works. So it's not that, it's true that D3 brain is special in this sense, right? But okay, you may lose some of this, and the idea may still hold. Okay. Any other questions before we go into this? Are you particularly tired now, or okay? All right. Good. So let me write the metric for a generic DP brain. So this again is the string frame metric. If you don't know what the string frame is, we discuss it after the lecture. It's just a vile rescaling of that action I wrote there. So it looks something like this. Well, with this, I'm just denoting the P plus one dimensional Minkowski ball body. So you see, when P is 3, you have your 4 dimensions here, a radius square, and so if you want this, when P is 3, this is 5, so this is your 6-dimensional flat space outside the D3 brains. The dilaton that for the D3 brains was turned off, and actually is a parameter that you can fix to the number you wish. E to A2 dilaton is given by this. So you see, for P equal 3, you're okay in having a constant here. Actually, you may write that constant explicitly. It's just a constant. And there is an expression for the gauge potential in terms of 1 over h. So what I mean to say is that it's just that. So it's 1 over h prime and that differential. For those of you who cannot see it, there it was. Okay, so and now I should tell you what this function h is. So let me make what's a very interesting story, cut it short. This function h, in this case, a solution to the equations that will come here, is given in this form. Constant, integration constant, radial coordinate to the 7 minus b. Okay. So if you check for the particular case p equals 3, you will get that this function h is 1 over the radial coordinate to the 4, and hence the h to the minus a half will give you radial coordinate square. This gives you 1 over radial coordinate square, and this is the ADS5 we are writing yesterday.
You don't want a constant term in there?
Very good. So I don't. There is a possibility of adding here another integration constant that people naturally choose to 1 in order to have a space that is asymptotically Minkowski. The reason why I'm not putting it is because when you take this particular decoupling limit I was mentioning yesterday, you are basically erasing this constant. Okay, it's a bit more subtle than that, but that's what you're effectively doing. Okay. Let me say it in different words, perhaps confusing words, but different. If I keep this constant, I will be constructing a dual to the field theory I'm going to mention now, but coupled to gravity and stringy modes. Okay? If I erase this constant, and that's why the process is more subtle than just erasing it, and it's this decoupling limit introduced by Baldacena, I will be constructing a dual to the field theory I want to, right? Not coupled to gravity.
So you want the near horizon?
Yeah, exactly. Yeah. This is the near horizon, and you know it. Okay, right. So I didn't want to enter into this story in order to not confuse people who do not know this. All right. So just what is true is that this thing works. Okay. Okay. So there are a couple of things I should be saying about this kind of metrics. And let me say it here. That is the fact that the line p equals 3, or the value p equals 3, and again, notice that the value p equals 3 is kind of very important because the dilaton suddenly becomes a constant, right? And if you compute the Ricci scalar of this, it will give you, by the way, this, if you compute it, it will give you something like, let me see if I have it written here. It will give you something like this, right? So in the ADS5 case, the Ricci scalar will give you a constant, right? And in the p equals 3 case, it will give you a constant, but in all the other cases, it will give you something that is not, is changing. Right? So, you see this, I'm going to say something that I didn't insist enough, so that's why I'm going to say it quickly. That is the fact that this type 2B supergravity approximation, this is just the supergravity action, is a good approximation to the string theory, and this is something that I guess many of you know. It's a good approximation to the string theory whenever two things happen. One of them is that the string coupling is small in order to avoid quantum corrections, and the other is that the curvatures, the typical curvatures compared with alpha prime are small, in order to avoid what, as I'm guessing you all know happen, when you have an Einstein theory, you know the string theory corrects these Einstein equations with r to the 4 terms or higher, right? So in order to avoid those terms to be relevant, you will impose that your geometry is weakly curved, right? So in other words, what I'm saying is that if you're considering a solution of this kind, but your geometry is somewhat very strongly curved, there is no reason why you should not have considered these terms. Okay? Is this clear? right? So in order to keep yourself within the approximation you want to work with, you would like to impose that this is small and this is small. All right? This thing, as many of you may know, is related to the value of e to the dilator. And this thing, well, is just something that you compute. So it happens that in order to keep yourself within this approximation, this background I was writing there has some kind of a range of validity. These generic backgrounds have a range of validity. So let me draw here a radial coordinate. And this is going to be for this is going to be valid for p plus 1 smaller than 4, and this is going to be valid for p plus 1 bigger than 4. So here I will be considering the case of B0, B1, B2 branes, right? And here I will be considering the case of B4, B5, B6 branes, B7 branes also. This case is not going to be considered within that kind of solution. So let me not put this one here. So what happens is that there are two scales. One will be scale where the dilaton becomes bigger than 1, and the other is going to be a scale where the Ricci scalar becomes bigger than 1. Okay? And I should, in order to keep myself within the approximation where these solutions are obtained, I should try to avoid going over those scales. So these scales are like this. Let me call it lambda 1 and lambda 2, and here lambda 2 and lambda 1. The scale lambda 1 is associated when the dilaton goes bigger than 1, or the string coupling goes bigger than 1. The scale lambda 2 is associated with the fact of the typical curvature going bigger than 1. So if you can see it here that for p bigger or smaller than 3, whatever happens to this function is the opposite, right? So that's why these scales, lambda 1, here is a low scale and here is a high scale. Okay, I hope this is clear. If not, please interrupt me. And similarly with this, right? So for p bigger or smaller than 3, it will make that this is becoming of order 1 at a high or at a low scale. Okay. Okay, let me see what I want to say about this. Okay, very good. So, and it is within this regime that this type 2A or type 2B metrics and configurations are good. All right? Is this more or less clear up to here? If not, let me pause 1 second because now is coming the physics bit of it. If there is something here that you would like to ask or emphasize or whatever, ask now. That's a good point. Okay. Yes? Good. Very good. So, you see, what's happening here is the following. Let's consider systems that are, let's call them lower dimensional systems. That is, field theory in 0 plus 1 dimension, so like a quantum mechanics, that's what happens in a D0 brane. Theories in 1 plus 1 dimensions, or theories in 2 plus 1 dimensions, right? Those theories, as we discussed here, are theories that, in lower dimensions, those are theories whose infrared is complicated and strongly coupled, but whose ultraviolet is very weakly coupled. Right? Good. So, the good description of this system, and by the way, this touches with something quite interesting. This radial coordinate will be associated with an energy coordinate in the field theory. Same here. Okay. So you see, taking theories in 2 plus 1, 1 plus 1, 0 plus 1 dimensions, those theories at high energies, they are weakly coupled. Okay? So the best description of whatever is your system that is related to a 0 plus 1, 1 plus 1, or 2 plus 1 field theory, if you take it at high energies compared to some characteristic scale, those degrees of freedom are your good degrees of freedom, are your perturbative degrees of freedom. So they are the ones that will take the system here. Here, you will compute with your gauge field, your scalars, and your Fermis. In theories that are in dimension 4 plus 1, 5 plus 1, 6 plus 1, etc., it's the opposite from what we said. Those theories are easy to compute in the infrared. They are perturbative, so they will take this region of the energy range. Okay. So, if you want to say it in this way, you have a type 2b or type 2a description, you start pushing it to the infrared, and that means to lower values of the radial coordinate, and in this case, your Ricci scalar suddenly will become of order 1. You should not trust anymore this description, and you should move to another weakly coupled description in terms of gauge fields and fermions and scales. You have a type 2a or type 2b description of a lower dimensional system. You push it to the ultraviolet. At some point, your Ricci scalar will become of order 1. Don't trust it anymore and start computing with gauge fields, etc. That will be weakly coupled. Here comes the trick of the string theory now. You have a lower dimensional system and you start pushing it to the infrared. Okay? Suddenly, you reach this point where your dilaton will become bigger than 1. Okay? So there are two things you can do here. And this is just stringy stuff, so those of you who are not stringy, just faith believe this thing. If you are in type 2A, you could go to M theory, right? To 11-dimensional supergravity or M theory. That's the way type 2A protects itself about strong coupling. If you're in type 2B, you just do an S-duality that just flips the sign of the dilaton. So it makes the e to the phi large into e to the phi small. Okay. So if you are, so here you will either go to M theory or do an S-duality, depending on the fact that if you are dealing with D0 brains, that's type 2A, you will go to M theory. If you are dealing with D2 brains at type 2A, you will go to M theory. If you are dealing with D1 brains, you will do an S-duality. And so you see, your infrared description of the system will be either an M theoretical description or a type 2B description in terms of the same variables, but where the dilaton, that offending thing that was bothering you, now is weakly coupled. Okay? But let me say it in this way. Let me point this. Your infrared description here is no longer field theoretical, if you want to say it in this way. So the string degrees of freedom enter to say the gate. Okay? So something very non-trivial happened in here. Here is the same. Notice that I'm calling this lambda 1 and lambda 1 for the same reason. Either you do an S-duality, and that will happen if you are dealing with D5 brains, or you go to M theory. And that will happen typically if you are working with D4 or D6 brains. Okay? The point that I want to emphasize this, for some reason, this is an idea that I like a lot, and I never able to convey it in its full glory. I always get the impression that people don't get what's going on here. They don't appreciate what's going on here. But notice that, let me say, notice that what's happening here is a renormalization group flow of the degrees of freedom. Right? Here is crystal clear, the thing. Let me compare it to the n equals 4 case. And this, Arshun, I think this will go over your point, right? Because in n equals 4, I had one parameter that was this top coupling lambda. If the top coupling is very small, say that 1 is here, well, I'll better describe things in terms of gauge fields and fermions and scalars. Right? These are my weakly coupled degrees of freedom. But if lambda is very large, I'll better work in terms of supergravity on ADS phi versus phi. In the middle, I'll have to work with the full string theory. Okay. Well, here the thing is more interesting. Here, you move yourself from string theoretic to field theoretic degrees of freedom, right? So this is a 10-dimensional description. This is a 0 plus 1 or 1 plus 1 or 2 plus 1 description. Similarly here, you move from a 10-dimensional description to either string description or an M theoretical description and a field theoretical description in 4 plus 1, 5 plus 1, etc. But what we see here is a Wilson normalization group flow of the degrees of freedom, right? How the degrees of freedom mutate themselves into something else. Is this idea more or less clear? Because if it is so, all the extensions to go into more appealing theories just resort on this idea. Then technically one is nicer than the other or depends on taste, but the idea I would say is this one.
But there's no dilaton in M theory, so what happens? Suppose you were on the M theoretic description.
Right, very good. So suppose you jump here to the M theoretic description.
Yeah.
You have no dilaton, you gain one dimension,
Mhm.
and so let me draw it here. So suppose that you have a type 2A metric like this one. Right? So suppose you happen to be in type 2A. Right? So what will happen is if you go to a theory, I'm going to quote the formula that you know. If you are to lift that to M theory, what will happen is that the metric will look in this form. This is your extra dimension. Right? And if you happen to have one form, that is, if you happen to have these 0 branes, p equals 0, this will. And this is your 10D metric, the one that I was writing there. By the way, these factors are like this. Okay. So indeed, there is no dilaton in M theory. What you gain is a dimension. This is just a word factor now. You don't call it dilaton. Okay. If you happen to have an A with P equals 2, so that is, if you happen to have either the 2 or the 4 branes, you will gain this. You know very well. This field in M theory that will be related. Okay. If you happen to have an H field, well, a Neves-Schwarz field, you will also gain one of these in this form, etc., etc. Right? So the prescriptions to lift. So I don't know if I understand your question, right? So all I'm saying is
No, so the parameter now is just the geometric size of the
Yeah,
extra.
yeah,
sum.
yeah, exactly.
The only thing that-
And if you happen to have this size very small, then you can go to type 2A with no problems. Okay. Any other questions?
Yeah,
Please, please.
one small thing, I was a little confused. So here alongside the first line, the return will decrease as you increase rho.
Yes.
And I mean R will increase, right?
Yes. No.
Yeah.
Okay. So
This is what
let's copy this.
this is just
into a
exponential.
dilaton.
Yeah.
Is
Is
1
like
over rho
1 over
7 minus p
whole
p
to
minus
the
p. No.
yeah. Whole yeah.
Is it good?
Right.
So
this
larger
is going
rho.
to yeah. And
So this is positive for p.
yeah. So I mean yeah. This I mean just the fact that you wrote down lambda 1 was I mean exponential phi greater than 1 was a little not natural, but yes.
Okay, so the dilaton is going to do something. This is where this is situated.
This is
where this happens.
yeah, sure.
Good.
Yeah.
This is
So,
for the richest
Yeah.
scale.
So one would increase and one would decrease. That's
Yes.
why you have a
Yes.
region in
Yes.
between where.
Yes,
Yeah.
yes. So the richest scalar does something like this.
Yeah. Right.
So,
Yeah.
yes. All right. And this is
your region of And in string theory, this is in theory of S duality. That's yeah.
Okay. Any other questions or comments about this? So I hope we are all more or less comfortable with the fact that there could be a flow in degrees of freedom, and this is very similar. Actually, it's the same as a Wilsonian normalization group flow, and very interesting, very important point to be emphasized here is that this radial coordinate is somewhat telling you that this is an energy coordinate. Okay. So remember that I was insisting when we wrote ADS5 cross S5 to write it in terms of a U coordinate that I was saying has units of, contrary to a radius coordinate, has units of 1 over length or has units of mass, so has units of energy, right? when you do things carefully in this perspective, this radial coordinate will also have units of energy, etc. And that's why it's very good to think it that way. Any other questions or comments? Let me see, what's the time?
So you could say that in this, what you're doing is geometrizing the normalization group flow.
Yeah.
You're giving it some
Yes.
geometric meaning, and then having
On the spot.
having some sort of geometric theory describing.
So the metrics and their completions, right? By completions I mean either do your S duality or your Lifton theory, or vice versa, are geometrizing the Wilsonian flow.
So Wilson should have discovered it.
There are two very recent papers, one by Polchinski and student, and one by Hong Liu, Mukund Ragamani, and someone else whose name I don't remember, where they're making this point even more concrete. Even more concrete. They are dealing with the Wilson equation, right? So the thing is really is a flow. So and this idea of the flow will be hyper present in the next tableau. Okay. So 5 to 11 break.
Yes.